Good morning, class. We are looking at exam 4 review, chapter 4 application of differentiations, chapter 5 integrals, and 6.1 area between curves. So in this part, we're going to cover 4.9 antiderivatives, 5.1 areas and distances. So first, as far as anti-differentiation, the reverse process of integration is concerned, the derivative of kx is k. Therefore, the integral of k dx must be kx plus c. Bear in mind that this is the reverse process and k is a number. The power rule, the derivative of x to the power of n is nx to the power of n minus 1. So the integral of x to the power of n dx must be x to the power of n plus 1 over n plus 1. And of course, a constant n can be negative 1 because the denominator can't be 0. And so here's the process that makes some sense out of it. If we look at the derivative of x to the power of n, the power rule, first we multiply by n, then we subtract 1 from n for the exponent. So the reverse process is going to go this way. If I want to integrate that, I'm going to go with the reverse process. So 2 becomes 1, and instead of subtraction, we're going to add 1. And for 2, instead of multiplication, we're going to divide by n plus 1. And that's why we have this one. And by the way, if you differentiate this one, you should get x to the power of n. When we look at the derivative of e to the power of x is e to the power of x, then the integral of e to the power of x, of course with dx, must be e to the power of x and a constant. The integral of 1 over x must be ln x and a constant. The integral of cosine must be sine and a constant. The integral of negative sine is cosine x and a constant. So the integral of sine is minus cosine and a constant. So it's the reverse process. Same thing with tangent, cotangent, secant, and cosecant. Since the derivative of tangent is secant squared, the integral of secant squared dx must be tan x. The integral of cosecant squared must be minus cotangent x plus a constant. The integral of secant tan dx must be secant x and a constant. The integral of cosecant x cotangent x must be negative cosecant x plus a constant. The constant multiples. So if you have a number, whether it's inside or outside, the integration sign makes no difference. If you recall, differentiation was the same thing. Sum and difference, basically, they mean when you are integrating or differentiating for that matter, do them term by term. And so the derivative of e to the power of kx, we know we write the same thing, we multiply by k. So the integral, we write the same thing and we divide by k, and of course a constant. That's the way it should be. So I believe it's pretty straightforward as far as how we arrive at this. Find all functions g such that g prime is 4 sine x plus 2x to the power of 5 minus square root of x over x. Solution. Sometimes you will need to simplify first. Factor, cancel, remove radical notation, etc. Sometimes you will need to integrate using substitution. So what we are going to do, we're going to make up 2 fractions here, first and foremost. This one gives us 1 fraction. This one gives us another one, and square root of x is the same as x to the power of 1/2, and this is x to the power of 1. And what we end up with is 4 sine x plus 2x to the power of 4 minus x to the power of negative 1/2. We put it in this format so we can use the power rule on that. So we're going to integrate the right side times dx. The derivative of sine is cosine, but the integral is negative cosine. So that's why we're going to have minus 4 cosine x. 2. We're going to divide by 4 plus 1, so 2 over 5 x to the power of 5. So 4 cosine x plus 2 over 5 x to the power of 5. And then we're going to use the power rule on this one also, minus 1 over negative 1 half plus 1, x to the power of negative 1 half plus 1, and a constant. So again, 2 divided by 4 plus 1 minus 1 divided by negative 1 half plus 1. Now negative 1 half plus 1 is 1 half. The reciprocal is 2. And the final answer therefore becomes negative 4 cosine x plus 2/5 x to the power of 5. This thing changes to minus 2 squared of x plus a constant. We are going to integrate 2x to the power of 4 for 3x cubed minus 7x squared plus x minus 5 dx term by term. So this is 2 over 5 x to the power of 5. Plus 3 over 4 x to the power of 4, because we are adding 1 to the exponent and we are dividing, right? So take a look at this. Minus 7 divided by 3, minus 7/3 x cubed. Notice this means x to the power of 1. So we add 1 to it, becomes 2, plus 1 half x squared, and finally minus 5x, and a constant. Bear in mind that the independent variable is x. X minus 5 quantity squared. First, we raise it to the power of 2. We get x squared minus 10x plus 25 dx. This one is 1/3 x cubed. This is minus 10 halves. Minus 10 divided by 2. Remember, this is 1, so 1. Minus 10 divided by 2. Minus 5x squared. Finally, 25x and a constant. Whether we want to differentiate or integrate, the first step is the same algebraic technique. We are going to make up 3 fractions. This is 1 minus 7 over x, 2 over x squared. For the sake of the next step, which is integration, minus 7 over x, we're going to write it as minus 7 times 1 over x, and 2 over x squared, we're going to write it as 2x to the power of negative 2. And 1, because this is dx, gives you x. Minus 7, 1 over x gives you the natural log. So minus 7, ln of absolute value of x. And this one, let's quickly look at that one using the power rule. 2 divided by negative 2 plus 1, x to the power of negative 2 plus 1. I hope you recognize negative 2 plus 1 as negative 1. So 2 over that makes it minus 2, x to the power of minus 1. Therefore, minus 2 over x plus a constant, because we're not going to have a negative exponent. The integral of 1 plus cosine t dt, bear in mind the independent variable is t, so 1 gives you t. Cosine, the derivative is negative sine, but the integral is positive sine t plus c. Positive sine t plus c. The integral of cube root of x minus sine x dx, first and foremost, we're going to change this to x to the power of 1/3. Therefore, we can use the power rule on that. 1 over 1/3 plus 1, x to the power of 1/3 plus 1. Minus, the derivative of sine is cosine, but the integral is negative cosine. So minus negative cosine and a constant. We are looking at this one, everybody. And so what happens here is that this is 4/3. The reciprocal of that is 3/4. Now 3/4 x to the power of 4/3, we write it as 3/4 cube root of x to the power of 4. Negative and negative gives us positive, and a constant. Again, we are going to cut this into two fractions, this one and this one, by changing this to x to the power of 1/2. So this changes to x to the power of 1/2, x over x to the power of 1/2. This is x to the power of 1/2 because the exponent is 1, everybody. And we don't have an exponent, the exponent is 1. It's not 0, just be careful. 1 minus 1/2. So it's x to the power of 1/2, this is x to the power of negative 1/2. And now we're going to use the power rule on this. So the first one, 1 over 1/2 plus 1, x to the power of 1/2 plus 1. The second one, 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and a constant. 1/2 and 1, they add up to 3/2. Now, when you divide by 3/2, that means multiplication by 2/3. Negative 1/2 and 1, they add up to 1/2. And remember, division by 3/2 is multiplication by 2/3. Division by 1/2 is multiplication by 2. And we get 2x to the power of 3/2 over 3 plus 2x to the power of 1/2 plus c, and we are done. The integral of x squared plus 2 over x squared plus secant squared x. To do this, first and foremost, we are going to change this part into two fractions. This gives us 1. This gives us 2 over x squared. And I hope you remember we've done this before. This one from the previous page is 2x to the power of minus 2. And we went over that, and I showed you the answer for that one is minus 2 over x. But in any event, let's do this again step by step. And that means the first one, because this is dx, the answer is x. The second one, if I want to integrate this, I'm going to divide it by negative 2 plus 1 x to the power of negative 2 plus 1, which makes us 2 over negative 1, so minus 2x to the power of negative 1, or minus 2 over x. And as you recall, the integral of secant squared is tan x, because the derivative of tan x was secant squared. So we are going to have tan x and a constant. Solve the initial value problem where dp dt is 2e to the power of 3t and p of 0 equals 1. So the question is, what is an initial value problem? Any equation containing a derivative is called a differential equation of d. A function which satisfies the equation is called a solution to the differential equation. An initial value problem is a differential equation along with a specified value of the unknown function called the initial condition. So for now, I want you to ignore the concept of an initial value problem for now. And we're going to concentrate on this, which means dp is 2e to the power of 3t dt, and we are going to integrate both sides and what we have been doing so far, nothing brand new yet. And so the left side, of course, becomes a p of t. And this one, as you recall, if you're, so that's what we're doing. As you recall, if you're differentiating, you multiply by 3. If you're integrating, you divide by 3. So 2/3 e to the power of 3t plus c. So what we have is just as before all the previous pages, and this is known as a general solution. Or even family of functions. What happens here, because of this constant, we are looking at indefinite integral, and this gives us a general solutions. It's a family of functions. There are infinitely many solutions because the constant can be any number. However, the initial value problem give us a pair, in this case 0, 1. If you replace the independent variable, which is t in this case, with 0, and the independent, which is p of t or y, with 1, you can find the missing value of c. So e to the power of 3 times 0 is e to the power of 0, which is 1. And so 2/3 and what number they add up to 1, c becomes 1/3. And the function from general solution goes to one solution called particular solution. So we have infinitely many solutions here. We've been doing the integration so far. It's the same as this one. When a pair is given, we can find the value of c and becomes one of those functions, which is a particular solution based on the given initial value. Here's another example. We want to solve this where y is 5, x is 1, which means the pair 1 comma 5. And so dy is the right side times dx. If I integrate the left side, I get y, and the right side, we're going to work on it. So in order to work on this, this is fine. This we are going to change it to x to the power of 1/2, comes up, becomes negative. So this gives you simply ln of absolute value of x. But what about this one? 1 over negative 1/2 plus 1 x to the power of negative 1/2 plus 1 and a constant. So this is this one. And so this one is 1/2. The reciprocal is 2. And x to the power of 1/2 means square root of x. Now, again, what we have is a general solution, everybody, because we have a constant. Now, we have a pair 1 comma 5. If we plug in, we can find the value of the constant. So let's plug in x equals 1 and y equals 5. As you know, ln 1 is 0. This is 1. So you're saying 2 plus what number is equal to 5? The answer is 3. And now this is a particular solution, because we went from a general solution, a family of solutions, infinitely many solutions, to one of those solutions with the help of a pair 1 comma 5. Here's an application of that rectilinear motion. A particle moves in a straight line. and has acceleration given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals negative 6 centimeters per second, and its initial displacement is s of 0 equals 9 centimeters. Find its position function, s of t. So first, reminding you of rectilinear motion. For motion in a straight line with constant acceleration a, initial velocity v sub 0, and initial displacement s sub 0, the displacement after time t is given as s of t equals half of at squared plus v0t plus s sub 0. This is what we learned in physics, basic physics. I hope everybody remembers that. So we are going to move on. All right, so let's see what's given and what needs to be done. A of t is given. A of t, acceleration, is v prime of t. The first derivative of the velocity function and the second derivative of the position function s of t. So if you differentiate this, you get the velocity function. If you differentiate it again, you get the acceleration function. Half of a is the acceleration. If v sub 0 represents the initial value or the velocity, s sub 0 represents the initial value or displacement or the position. And so we are going to integrate this. So this is an easy case. Let's write the antiderivative of this to get to v of t, which is 6 halves or 3t squared plus 4t and a constant. So we are integrating this. We are writing the antiderivative, a general solution. Because v of 0 is minus 6, if I replace the t with 0, I can find the missing constant. So if you plug in t equal to 0 here, you get c. On the other hand, v of 0 is 6, so you get negative 6. So c must be negative 6. Again, one more time. Just replace it. If you want, you can show board. So v of t, so if I put 0 here, I get 0 plus c, and I get 6 here, so that's the proof. Minus 6, I mean. And that's the proof that c equals minus 6. And so this is your velocity function. Now, to find s, you have to integrate this or write the antiderivative again. I hope you recognize this. 3 divided by 3 is t cubed plus 2t squared minus 6t. I'm not going to write plus a constant. I'm going to write something else like the if you write it c sub 1, c sub 2 is fine. And if you write c, it's okay, but we don't want to be under the assumption these two are the same. That's why it's just some constant. And we know s of 0 is 9, that is given. So if I replace the t with 0, I get 0 here, 0 here, 0 here. And I get d, which must be 9, therefore makes d equals 9. And the general solution becomes a particular solution. S of t is t cubed plus 2t squared minus 6t plus 9 because of this initial value given. This is known as a rectilinear motion. Another application example, a sample of cesium-137 with an initial mass of 79 milligrams decays t years later at a rate of negative 1.8249 e to the power of negative 0.0231 t milligrams per year. find the mass of the sample after 23 years and round it to 1 decimal. So what this is the initial value and this is the rate. This is the derivative of some function. So if m of a t represents the mass of cesium-137 after t years at any time t, then its derivative, which is m prime of t or dm dt, is this one with the initial value 79. So dm dt is this function. M of 0 is 79. So we are going to find m of t. And then we're going to plug in 23 to find m of 23. So we are going to integrate. So we're going to put the dt here and we're going to integrate. So m of t is the integral of this guy times dt. So you put the dt on this side and you integrate, and this is what you get. Now, as you recall again, e to the power of kx, you divide by k and you write the same thing. So it's the same thing. Divide this number by negative 0.0231 and a constant. This ends up being 79. So we write it. And we know m of 0 is 79. So if we replace this with 0, e to the power of 0 is 1, we get 79 equals m of 0. 79 e to the power of 0 plus c. This is 79. '79 equals 79 plus c. C must be 0. And this is the general solution, which now is changing to a particular solution. So general solution, infinitely many solutions. Now we have a particular solution, one solution. What do we want? M of 23. Replace the t with 23. Put it into a calculator. And whatever the answer is, since we want 1 decimal, you look at this decimal. Next to it is number 3. That doesn't change. 46.4. And the units are milligrams. You always write with a bunch of decimals to begin with, okay? Let's go to 5.1, areas and distances, the method of exhaustion. Areas of familiar polygons, such as triangles and rectangles, enable us to find the areas of more complicated regions by filling the regions with increasingly smaller elements of known area. This is called the method of exhaustion. What are we talking about? In the old days, when they didn't know the area of a circle was pi r squared, they would inscribe a polygon, a three-sided, because they knew how to calculate the area of a triangle. And then they would add to the number of sides. As you can see here, when we add to the number of sides, the area of that polygon that you have gets closer and closer to the area of the circle that contains that. This is called the method of exhaustion. Now, the area problem follows the same way. So you have this. And you want to find the area under the curve. So find the area of the region S that lies under the curve y equals f of x from A to B. This means that S is bounded by the graph of a continuous function f. Here's the function f, where f of x is positive, greater than or equal to 0, non-negative. The vertical lines x equals a and x equals b, and the x-axis. Now, everything that is written here can be written in this format, nice and easy, in mathematical format. S equals the set of points x and y such that x is between A and B, y is between 0, because the x-axis has the equation y equal to 0, and f of x. So how do you find this area? That's pretty impossible, because we don't have any geometric shape and therefore geometric formula for it. So that's why we use the method of exhaustion. So what do? We cut it into so many pieces, okay? And if we use rectangular strips with equal width, it makes it easier to deal with. So in this case, we cut it into 4, but in general, we cut it into n. So delta x, this width is delta x, b minus a over n, and we use this Riemann sum. So we have this Riemann sum, the summation of I going from 1 to n, f of x of I delta x equals f of x of 1 times delta x plus f of x of 2 times delta x all the way to f of x of n times delta x, where delta x, or the width, is b minus a divided by n, meaning this distance is delta x, same as this distance. And again, they don't have to be the same, but if you choose them to be the same, it makes it easier to deal with. Okay, it makes it easier to deal with. Now, what do you do with those rectangular strips? You have the width and it's precise, but what about the height? What is the height of this rectangle? You can use the left endpoints, right endpoints, the midpoints. It doesn't matter. It's an approximation. So if you use all the left endpoints, those are the heights. And those are the 4 rectangles you calculate. If you use the right endpoints, this one, this one, this one, and this one, you get this rectangle, this one, and this one. And you can use the midpoint, you name it. Wherever you go in between, f of the left endpoints or the right endpoints or the midpoints makes no difference. It's an approximation, it's not the answer. As we add to n, to the number n, we get a better approximation. So suppose a continuous function f is defined on the closed interval of a to b. If the interval is divided into n subintervals so that delta x is b minus a over n, and x sub 0 is a, x sub 1 is a plus delta x sub 2 is a plus 2 delta x, all the way to the last one, b, which is x sub n, or a plus n delta x, then a Riemann sum associated with f is the sum, the summation of I going from 1 to n of f of x sub I delta x, which is f of x sub 1 times delta x, all the way to f of x sub n times delta x. X sub I is any point in this subinterval of a sub I minus 1 to a sub I. So here's the geometry and procedure that is called the Riemann sum. Number 1, let's say partition A and A to B into 4. Just make up some numbers. Then make 4 rectangles. Width would be, the width will be b minus a over 4. And the heights are f of x sub 1, f of x sub 2, f of x sub 3, f of x sub 4, if we go with the right endpoints. Then change it to 8 or more rectangles. As the number of rectangles increase, the approximation gets better. That's the idea. So if you look at the left endpoints, the right endpoints, and the midpoints, they do have formulas. But I'm going to show you an easy way. You don't have to memorize this formula with setting it up using a line segment. The idea is that with the left endpoints delta x times the height would be f of x sub 0, f of x sub 1, all the way to the one before the last. For the right endpoints, we start with f of x sub 1, we go to x sub n, and this is the midpoint, the middle of the two. So area can be approximated with this formula. If you choose 4, for example, but the area is exactly equal to the limit as n goes to infinity of summation of f of x by delta x as I goes from 1 to n. So if you take a limit and let go n to infinity, this becomes the area under the curve exactly. Delta x is b minus a over n, and x of I is a plus I delta x. This represents the area under the curve if the function is positive. If it's not positive, it's the net area, the difference of areas. So for example, we want to use the left endpoints, the right endpoints, and the midpoints rule with n equals 5 to approximate the integral of 1 over x dx as we go from 1 to 2. So this integral represents the area under the curve from 1 to 2. If it's positive, if it's not, it represents the difference in the areas. Okay, so it's known as the signed areas. Now here's the formulas, and you really don't have to memorize that formula. You need to know the concept known as the Riemann sum. So first and foremost, we want to graph the function. The function is 1 over x. We're going to graph that, which you remember looks like that. And we are interested from 1 to 2. So the function is 1 over x. A is 1, B is 2. That means we want from 1 to 2, we want this area. And we are going to approximate it by cutting this into 5 regions, and we are going to approximate the area. We discuss the exact area later on, but that's the idea. So first and foremost, you need to find delta x. Remember, delta x is defined as b minus a over n. So b minus a over n, which makes it 2 minus 1 over 5, which is 1 over 5 or 0.2. Now, if you want to memorize that, so be it, not a good idea. So all you have to do, say from 1 to 2, here's from 1 to 2, we're going to cut it into 5. I made it large so we can see it. This is extremely small. So we can see we're going to go from a equals 1 to b equals 2. We're going to cut it into 5 equal parts. Each part is 0.2. So this is 0.2. This becomes 1.2, 1.4, 1.6, 1.82. Pay attention to this. Now we're going to use this formula for the left endpoints, for the right endpoints, for the midpoint. So how do we do that? If we want to use the left endpoints, remember, delta x is fixed at 0.2. For left endpoints, the height at this point, this point, this point, this point, this point, but not that point. That means we are going to use this formula, f of x sub 1 times delta x. So we're going to factor the delta x out. The delta x 1 over 5 or 0.2. And here's the function 1 over x. So we are going to put into 1 over x the very first point 1, so 1 over 1. Then the next one, 1 over 1.2. The next one, 1 over 1.4. The next one, 1 over 1.6. The next one, 1 over 1.8. This gives the height. But why aren't we using 2? Because we are using the left endpoints, and I'm going to use L to represent left, and I'm going to use 5 because n is 5, L sub 5. You put it into a calculator and you put it with a lot of decimals. Now for the right endpoints, you're going to write the same thing. Now R5, 1 over 5, you don't use this one. You start from, because you're using the right endpoints, remember that. So 1 point to the right side, 1, 2, 3, 4, 5, there are 5 pieces. So you put 1 over x, that means 1 over 1.2, 1 over 1.4, 1.6, 1.8, 1 over 2. That's what you put in. And the calculation actually is simple because this part actually is being repeated. This part is the same as this part, everybody, okay? So if you did the calculation here, just have to add a 1/2 to the parenthesis. So anyways, you do the math, you end up with this number. Again, the two numbers are different. And the area is somewhere between the two. Now, these two are the approximation, okay, for the area. And we put so many decimals. What happens with the midpoints? For the midpoints, again, I don't want to memorize any of this formula. I'm going to find the midpoints as follows, everybody. Let's see. So here's the midpoint, the first one. Clearly, it's between 1 and 1.2, which makes it 1.1. The second, the third, the fourth, and the last midpoint. And all, I hope you recognize 1.2 and 1.4 in between is 1.3. Just add the same delta x, which is 0.2. So if this is 1.1, this is 1.3. This is 1.5. This is 1.7. This is 1.9. Just add 0.2. So let me just write them. So the next one is 1.5. The next one is 1.7. The last one is 1.9. So this can be approximated by this, or the midpoint, which is delta x times f of 1.1, 1.3, 1.5. So over here, I'm showing you that we used f of those, which is delta x replaced by 1/5 or 0.2. F of 1.1 means 1 over 1.1. F of 1.3, f 1 over 1.3 all the way to the end. And again, with a bunch of decimals, I didn't put as many, maybe I should have, but this is, as you can see, between the two. Midpoint gives you midpoints. They result in a better approximation than the left and right endpoints. But I hope everybody's clear as to what's going on. Antiderivatives as areas. The velocity of a moving object is given by the function v of x equals 3 times x, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled during the first 3 hours from 0 to 3. So as you know, y equals 3x is a line that goes through the origin, and we just want the first quadrant. So we want x to be between 0 and 3. So this is the area we want. This is the velocity function. This is the time. As you know, if it was a constant, the distance would be r times t, the rate or the speed times the time. But it's not. It's a function of x. Okay. So if the velocity was just number 50 miles, that's why they say on the average, maybe the velocity is this or that. And that being the case, we are going to find the area by using the fact that area of any triangle is half of base times the height. So when you look at this point, it has coordinates 3, and 3 times that 9. So this distance is 3, and this distance is 9. This is not too scale, class. This distance is 3, this distance is 9. As you know, it's a right triangle, so the base and the height would be the legs, half of 3 times 9, 27 halves, or 13.5 miles. Between the third and fifth hour, so between the third and fifth hour, so we want this area, and you have two choices. One would be just use the triangle from 0 to 5. Remember this point as coordinates 5. Let me just write that so it becomes easy for everybody to see. You could do that, this point as coordinates 5, and then remember v is 3x, so 3 times that 15. So you can calculate in the same manner the total area and then subtract this area that you have. Okay, that's perfect. So one more time, the area would be half of this number, which is 5, times half of this number, which is 15, and subtract that. That's one way to do it. The other one is that this is a trapezoid, and the formula for the trapezoid is half of the height times b1 plus b2. I hope you notice that when we look at it this way, this is the height, this is the smaller base, this is the larger base. So half the height is from 5 to 3. This is the height, everybody, of the trapezoid. 5 minus 3, or 2. So half of 2. And then this base, remember this was 9 and this is 15. So 9 and 15. And 2 and 2 cancel each other. 9 and 15 is 24 miles. Like I said, there are different ways of approaching it. This is one way to do so. Use the definition to find an expression for the area under the graph of f as a limit. Do not evaluate the limit where f of x is equal to x squared plus square root of 1 plus 2x, and x is a number between 4 and 7. Find delta x and x of I, and so forth. Remember, the area under the curve has this formula: the limit as n goes to infinity of the summation I from 1 to n of f of x of I delta x. So they want us to write this expression where delta x is b minus a over n, x sub I is a plus I delta x, and delta x is b minus a over n. So that's the idea. We want to write this. So we are going to go from a to b. So a is 4, b is 7, and delta x is b minus a, 7 minus 4 over n. So a is 4, b is 7, delta x is b minus a, 7 minus 4, or 3 over n. So that's delta x first. X sub I is a plus I delta x. So a 4 plus I times delta x 3 over n. X sub I is a, replace it with 4, plus I delta x, replace it with 3 over n. So I hope you see how simple it becomes. And the area is the limit of the left endpoints, the right endpoints as n goes to infinity. The right endpoints, you can write it in this fashion, where x sub I is this, 4 plus 3i over n, and f of x is this. So according to this formula, all I have to do, take a limit as n goes to infinity of the summation I going from 1 to n. I write f of x sub I times delta x. I have the delta x as 3 over n. What is f of x sub I? If this is f of x, then what is f of 10? Plug in 10. F of 20, plug in 20. F of a, plug in a. F of x sub I, replace the x with x sub I, which is 4, plus 3i over n. Therefore, f of x sub I is 4 plus 3i over n quantity squared plus the square root of 1 plus 2 times this expression. So that's f of x sub I. One more time, x squared means 4 plus 3i over n quantity squared plus square root of 1 plus 2 times x. That means 2 times this expression, 4 plus 3i over n. Now I'm ready to plug into this. F of x sub I is this expression, and delta x is this expression. And I'm done. So A is the limit as n goes to infinity of the summation I going from 1 to n of this expression we just found, which is brackets 4 plus 3i over n quantity squared plus the square root of 1 plus 2 times 4 plus 3i over n times delta x, which is 3 over n. That's all they wanted us to do, just to come up with that. So in essence, they gave us the region. They want us to come up with the area using the Riemann sum. Now, determine a region whose area is equal to the given limit. Do not evaluate the limit. The limit as n goes to infinity of summation of I going from 1 to n, 3 over n squared of 1 plus 3i over n. So this is in essence the reverse process of the previous example. We are given this, and we need to go through this process to find the function and the limits a and b in essence. Okay, so we're going to go through that. So we're going to repeat this as before. We're going to write a is the limit of r sub n as n goes to infinity. It's equal to that, and we're going to compare and contrast to figure out everything we need. So remember, this is the product of f of x sub I and delta x. Delta x may be written in front. Okay, so seems to me that 3 over n is delta x, and this one is f of x sub I. Again, compared, this seems to be f of x sub I, this seems to be delta x. If so, we know delta x is b minus a over n, and it's equal to 3 over n. And we know x sub I is a plus I delta x. So we're going to write these two expressions. Delta x is b minus a over n. That means 3 over n. And x sub I is a plus I delta x. Here's x sub I, everybody. And so we're going to write I 1 plus, instead of writing 3i over n, I want to separate them as I times 3 over n because I want them to look like that. So if this is delta x, 3 over n, so far so good, everything looks good. This must be a, and this must be b minus a. So b minus a is 3 from here, a is 1 from here. So if a is 1, b minus a is 3, b must be 3 plus a, which makes it 4. Therefore, the function y or f of x must be the square root of x and the interval of the closed interval of 1 to 4. So 1 to 4, and the function must be square root of x. Because remember what we are going to do? We are going to replace the x. In order for you to go to f of x sub I, you're going to replace the x with x sub I. So if you put this one here, you get a plus I delta x, which is this one. And you're done. However, it's important to know sometimes this is not unique. For example, when delta x is 3 over n, if you say x sub I is 0 plus I delta x, which is 3I over n, that makes A 0 and B 3. And how could that be? We have a 1 here. Then the function must be square root of 1 plus delta x. If you go this way, and instead of square root of x, if you have square root of 1 plus delta x, and instead of 1 to 4, we're going to have 0 to 3, take a look, and you can expand it to make sure it works. This one works also. So this thing may not be unique. That's the difference between the two. Example 20, the velocity graph of a car accelerating from rest to a speed of 120 kilometers per hour over a period of 30 seconds is shown. So in seconds, over the course of 30 seconds, it gets to 120 kilometers per hour. Estimate the distance traveled during this period. Use m sub 6, that means the midpoint, to get the most precise estimate rounded to 2 decimals. So first of all, what are they asking? They want you to calculate this area. But because it doesn't have a geometric shape we are familiar with, they want us to estimate it. You can use the left endpoints, the right endpoints, but they have specifically asked for m sub 6. Here's the formula, and you don't have to memorize it. What is important to know, m sub 6, that means you're going to cut this into 6 equal parts. That means 30 divided by 6. So delta x is b minus a over n. And that means 30 divided by 30 minus 0 divided by 6 is 5 seconds. This goes from 0 to 30. So delta x is b minus a over n. And this is 5 seconds. So we have this 30 seconds every 5 seconds, 5, 10, 15, 20, 25, 30. That's the idea, everybody. We also have to pay attention to the units. This is kilometers per hour, but this is in seconds. So we have to convert accordingly. So because this is kilometers per hour, we're going to go this with hours. As you know, 1 hour is 60 minutes. A minute is 60 seconds. So 1 hour is 3,600 seconds. We should know that. So delta t, which is 5 seconds, we need to know how many hours it is. In order to know how many hours, we are going to divide by 3,600. So delta t of 5 seconds is 1 over 720 hours, because 5 divided by 3,600. See, 5 goes away, 0 goes away, multiply 360 by 2. You know how it's done. 1 over 7/20th of an hour. So again, why did we do that? Units must agree. So we are going to go from a equals 0 to b equals 30 and 5 seconds. So 5, 10, 15, 20, 25, 30, or 5, 10, 15, 20, 25, 30 seconds. And each distance of 5 seconds corresponds to this many hours. So this is the delta x, everybody. Okay, so delta x, or whether delta t, because it's t is delta t, everybody. Delta t is 5 seconds. It's hard to read it. 5 seconds. With proper units, 1 over 720 hours. Now, that means we want to cut this into 6 equal rectangular strips. we are going to use this formula, delta x times f of x of 1 bar. That means the midpoint, f of x of 2 all the way to f of x of 1. This is the general format. So where is the midpoint? The midpoint is here. Which means if the first one is 2.5, right? 5 seconds divided by 2 is 2.5. The next one, just add delta t, which is 5, 7.5. Then add 5, 12.5, 17.5, 22.5. Add 5, 27.5. That means you're interested in the height at this point, this point, this point, this point, this point. So that means you're looking at calculating the area for this rectangle, add it to this one, this one, this one, this one, and this one. So I hope you see the rectangles. Now we can calculate, because it's the width delta t, 5 seconds. We're going to use this number. 5 seconds, we're going to use these numbers, times the height at this point, v, the velocity at 2.5, v, the velocity at 7.5, and so forth. So that's what we have. This is delta t, 5 seconds. We are using it with the proper units. So at 2.5, again, you have to look at this. You have to do your best. It's about 31.25. This one about 66. This may not be exact, but it gives you an idea as far as the concept is concerned. So you have to read from the graph. You have to read all these heights from the graph. And the midpoint for this one is almost 120, it's 119.25. And if you add them up, you get 521.75 times. This is 0.725 kilometers. You don't have to worry about being exact as long as you understand the concept and you show your work, you're in good shape.